Alright, so I have been mute for such a while. Alright, okay, since it's default initialized, since the string is empty and contains nothing, so any attempt at accessing the data would result in undefined behavior. Yeah. Okay. Great. Yeah. Okay. Write a program that reads a string of characters including punctuation and writes what was read but with the punctuations removed. Oh, that's easy. Okay. So this is 3.10. 3.10 CPP let's include few types. So let's include. Okay, I should include string if I'm going to be using a string. CC type, and finally string. So with punctuation marks, so I'll use get line, right? String, let's copy this. Okay, so string input, then I will get line input, get line from cn and input. Read the string with punctuations, punctuation and spaces. Okay, so we read the string, then for char c from input, I can go if is punct. I hope that is the right way. Is punctuation is punct. Is punct C. If C is not punct, then we simply print it C, right? And at the end we add a new line. Okay, so let's try. Go say I am writing punctuation. What else is punctuation? Yeah, I'm writing a program on string. So this is gone, this is gone, this is gone, this is gone. Oh, great. Okay. Okay. Is the following const string? Oh, is the following range for legal? If so, what is the type of C? It is a const. It is a const reference, right? It is a const reference to char. So const char reference. Hey. Legal and the type will be char. Nope, you are wrong, my man. Oh, okay. Now I remember. Can I undo this? Is there a way to undo? Rotate. No. Let me paint it white. Yes, I have some brush. Then I go legal and the type will be I think this is okay. Legal and the type will be const char reference, right? Reference to okay, keep out auto reference to a const char, right. Const string are the answers in appendix. Dude, it was working. Hold up. There's the appendix. Default random library names and headers. Okay, basics. Alright. Appendix A. Generally don't know. Nope. Is there a way to jump? Can I jump? No. Okay, 15 and this. When does the number start? This is page B face and chapter 1, number 1. Okay, so number 1, so 30. So I have to add 29 to whatever the number comes. Okay, so I was on, seriously, it just okay, so 81 I was with 90 plus 29 is 119. Off by a little. Okay. Oh, off by 10 pages. So, okay. Legal and type will be. I think I should check it once. Okay, so I will try to assign C some value, right? And it should throw an error. Let's go. Yeah. Okay. String. Assignment of read-only reference. Read-only reference, that is const reference, right? So const char, and if I leave it, if I go const char and then reference, I think it should throw in the same error. Yeah, read-only reference, read-only reference. So this is the alright. C is a read only reference, that is const char reference. Okay, then we move on to library vector type. A vector is a collection of objects, all of which have the same type. Okay, every object in the collection has an associated index which gives access to the object. Right. A vector is often referred to as container because it contains other objects. We'll have much more to say about containers in part 2. To use a vector, we must include the appropriate header. In our example, we assume that an appropriate using declaration is made. Okay. A vector is a class template. C++ has both class and function templates. Writing a template requires a fairly deep understanding of C++. Indeed, we won't see how to create a template until chapter 16. Fortunately, we can use templates without knowing how to write them. Templates are not themselves functions or classes. Instead, they can be thought of as instructions to the compiler for generating classes or functions. Okay. The process that the compiler uses to create classes or functions from templates is called instantiation. When we use a template, we specify what kind of class or function we want the compiler to instantiate. Okay. For a class template, we specify which class to instantiate by supplying additional information, the nature of which supply additional information, the nature of which depends on the template. How we specify the information is always the same. We supply it inside a pair of angle brackets. In class of vector, the additional information we supply is the type of the object we will hold. Okay. So IVEC holds objects of type int, holds sales items, and vector whose elements are vectors of string. Okay. In this example, the compiler generates 3 distinct types: the vector template, vector A, vector, and thus. Vector is a template, not a type. Types generated from vector must include the element type. For example, vector. Okay, types generated from vector must include the element type. Oh, right. Okay. We can define vectors to hold objects of most any type. Because references are not objects, we cannot have a vector of references. Okay. However, we can have vectors of most other reference built-in types and most class types. Okay. In particular, we can have vectors whose elements are themselves vectors. It is worth noting that earlier versions of C++ used a slightly different syntax to define vector whose elements are themselves vectors, or another template. In the past we had to supply a space between the closing angle bracket of the outer vector and its element rather than this. Some compilers may require the old style declaration for a vector of vectors, for example this. Okay. Defining and initializing vectors. As with any class type, the vector template controls how we define and initialize vectors. Table 3.4 lists the most common types. Okay, page 99. This is page 98. As with any class type, the vector templates control how we define and initialize vectors. We can default initialize vector, which creates an empty vector. Okay. Default initialization. It might seem that an empty vector would be of little use. However, as we'll see shortly, we can efficiently add elements to the vector at runtime. Indeed, the most common way of using vectors is to define an initially empty vector to which elements are added as their value become known as at runtime. Okay. We can also supply initial values for the elements when we define a vector. For example, we can copy elements from another vector. Okay. Oh, this will come in handy, right? Copy an element. Each element in the new vector is a copy of the corresponding element in the original vector. The two vectors must be of the same type. Okay, we can do this, and we can IVEC to error strings. Right. Alright. List initializing a vector. Another way to provide element values is that under the new standard, we can list initialize a vector from a list of 0 or more initial values enclosed in curly braces. The resulting vector has 3 elements. The first holds the string A. Okay. The second holds an, and the last is this. As we've seen, the C++ provides several forms of initialization. In many but not all cases, we can use these forms of initialization interchangeably. Okay. So far, we have seen 2 examples where the form of initialization matters. When we use the copy initialization, that is when we use equal to, we can supply only a single initializer. And when we supply an in-class initializer, we must either use copy initialization or use curly braces. Okay, list initialization, and this is error. Oh, parentheses. Right. Okay, so this is in class. Okay, in class, that is within class, we can supply only a single initializer. Okay, single. Okay, and when we supply an in-class initializer, we must either use copy initialization or use curly braces. A third restriction is that we can supply a list of element values only by using list initialization in which the initializers are enclosed in curly braces. Okay, in class initializer, page number 73 plus 29 plus 30, 103. Class data members defining what was it again? 200. Nope, overshot it. Hold up. Where am I? Where am I? Hmm. Hmm. Okay. So this is copy page number 73, and this is 127. Okay. I'll go to 73. 127. This is page number 73. So I just have to look for page number 73. 45. 45. How much should I add to get 73? 38. So 45 plus, okay, 74 plus 38 is 111. 70, okay. 73. Hmm. Okay. Oh, this initialization. Right. We can use this sales data with list initialization and this. Okay. Right. Okay. Cannot use parentheses. List of element in class initializer equal to copy. So this is also copy, right? Copy of elements. Take copy of elements from here. Creating a specified number of elements. We can also initialize a vector from a count and element value. The count determines how many elements the vector will have. The value provides the initial value for each of these elements. Okay. Value initialized. We can usually omit the value and supply only a size. Okay. In this case, the library creates a value initialized element initializer for us. The library's generated value is used to initialize each element. Library generated value. Okay, the value of the element initializer depends on the type of the element stored in the vector. If a vector holds an element of built-in type such as int, then the element initializer has a default of 0. If the element are of a class type such as string, then the element initializer is itself default initialized. Okay. There are two restrictions on this form of initialization. The first restriction is that some classes require that we always supply an explicit initializer. Okay. If a vector holds objects of a type that we cannot default initialize, then we must supply an initial value. Okay, page number 44. I was on 73. This is 44, right? Default initialized. Okay, we always have to. Okay. Types inside a function are uninitialized. The value of uninitialized variable are of built-in type. Each control how we initialize objects of class name. In particular, it is up to the class whether we can define objects of that type without an initializer. Okay, so there must be an explicit initializer. Most classes let us define object without explicit initializer. Such classes supply an appropriate default value for us. Okay, so there are sometimes default initialization, there is also explicit initialization. Okay, there are two restrictions. The first restriction is that some classes require that we always supply an explicit initializer. If our vector holds objects of type that we cannot default initialize, then we must supply an initial element value. It is not possible to create a vector of such type by supplying only a size. Okay. The second restriction is that when we supply an element count without also supplying an initial value, we must use the direct form of initialization. Okay. Must use direct initialization to supply a size. Okay. Here we are using 10 to instruct vector how to create the vector. We want a vector with a 10 value initialized elements. We are not copying 10 into the vector. Okay, hence we cannot use the copy form initialization. Okay. Must use direct initialization to supply a size. Okay. So ways to initialize a vector: a value, only the value. We have copy, equivalent of this empty vector. Then we have list initialization, and this. Okay. List initializer or element count. In a few cases, what initialization means depends upon whether we use curly braces or parentheses to pass the initializer. For example, when we initialize a vector from a single int value, that value might represent the vector's size, or it might be an element value. Right. Similarly, if we supply exactly two int values, okay, has 10 element with value 1, and it has 2 element with value 10 and 1. Okay. When we use parentheses, none. Okay. In a few cases, what initialization means depends on the initializers. Okay. When we use parentheses, we are saying that the values we supply are to be used to construct an object. Right? Great. When we use curly braces, we are saying that if possible, we want to list initialize the object. It does v1 and v3 use the initializers to determine the vector size and its size and element values respectively. v1, v2, v1 and v3. Okay, when we use curly braces, we're saying that if possible, okay, that is, if there is a way to use values inside the curly braces as a list of element initializers, the class will do so. Only if it is not possible to list initialize the object will the other way to initialize the object be considered. The values we supply when we initialize v2 and v4 can be used as element values. Okay. These objects are list initialized. The resulting vectors have 1 and 2 elements respectively. On the other hand, if we use braces and there is no way to use the initializers to list initialize the object, then those values will be used to construct the object. Okay. For example, to list initialize a vector of strings, we must supply values that can be used as strings. Right. Okay. In this case, there is no confusion about whether to list initialize the element or construct a vector of the given size. Okay, list initialization, then can't construct a vector from a string literal, right? 10 and 10. Okay, although we used braces on all, but one of the definitions, okay, v8 has 10 element. Okay, because this is not valid, but it uses this and replaces and considers it to use uses it as if these curly braces were parentheses. Okay, although we used braces on all but one of these definition, only v5 is list initialized, right? In order, the default 10 initialized, right? These two are the cases. Okay. In order to list initialize the vector, the values inside braces must match the element type. We cannot use an int item. We cannot use an int to initialize a string. So initializers for v7 and v8 can't be element initializer. If list initialization is impossible, the compiler looks for other ways to initialize the object from the given value. Okay. So we have which, if any of the following vector definitions are in error. Okay, this is okay. This is an error. Type miss match. Then this is okay. The string, and we are going, it has 10 elements and with string null. How many elements are there? How many elements are there? Okay. Let me go with it is, oh, this is very light. No? I need a little dark. It is too dark. What is the bro? How is this color not there? Cannot see the color. Okay, anyways. I'll start with this has 0, it has 10, and it has 2, and it has 10 elements. This has 10 elements, it has 1 element, and it has 10 elements. Okay, right, because this is 0, it has 10 elements. Initialization, this is the size, and this is the value of each element. Then this is list initialization. Sorry, I didn't mean to do that. I got none. Right, then we have because it is not valid, that we can have 10 as a value, so it sees and it updates, so it has 10 elements. It has 10 elements, it has only a single element. This is list initialized, and strings cannot have an initial value of 10, so it has 10 elements, as it uses that value to depict the number of strings. Okay. Adding elements to a vector. Directly initializing the elements of a vector is feasible only if we have the small number of known initial values. If we want to make a copy of another vector, or if we want to initialize all the elements to the same value. More commonly, when we create a vector, we don't know how many elements we'll need, or we don't know how the values of those, or we don't know the value of those elements. Even if we do know all the values, if we have a large number of different initial element values, it can be cumbersome to specify them when we create the vector, right? As an example, if we need a vector with values 0 to 9, we can easily use list initialization. What if we wanted elements from 0 to 99 or 0 to 999? List initialization would be too unwieldy. In such cases, it is better to create an empty vector and use a vector member named pushback member function pushback to add elements at runtime. The pushback operation takes a value and pushes that as a new last element on the back of the vector. Okay, for example, I is not 0, we get 0 to 99. Even though we know we ultimately will have 100 element, we define v2 as empty. Okay, each iteration adds the next sequential integer as a new element in v2. We use the same approach when we want to create a vector where we don't know until runtime how many elements the vector should have. For example, we might read the input storing the values we read in the vector. Read words from standard input and store them as elements in vector. Okay. Again we start with an initially empty vector, and this time we read and store unknown number of values in text. Alright. Okay, key concept: vectors grow efficiently. The standard requires that vector implementations can efficiently add elements at runtime. Because vectors grows efficiently, it is often unnecessary and can result in poor performance to define a vector of a specific size. Okay. The exception to this rule is if all the elements actually need the same value. If differing element values are needed, it is usually more efficient to define an empty vector and adds element. If differing element values are needed, it is usually more efficient to define an empty value and add value as we need become known at runtime. Moreover, we'll see here vector offer capabilities to allow us to further enhance runtime performance when we add elements. Starting with an empty vector and adding elements at runtime is distinctly different from how we use built-in arrays in C and in most languages. Starting with an empty vector and adding elements at runtime is distinctly different from how we use built-in arrays in C and in most other languages. In particular, if you are accustomed to C or Java, you might expect that it would be best to define the vector at its expected size. In fact, the contrary is usually the case. Okay. Programming implications of adding to a vector. The fact that we can easily and efficiently add elements to a vector greatly simplifies many programming tasks. However, this simplicity imposes a new obligation on our programs. We must ensure that any loops we write are correct even if the loop changes the size of the vector. Okay. Other implications that follow from dynamic nature of vectors will be clearer as we learn more about using them. However, there is one implication that is worth noting already. For reasons we'll explore, we cannot use a range for if the body of the loop adds elements to the vector. Okay. The body of a range for must not change the size of the sequence over which it is iterating. Very important. Okay. Write a program to read a sequence of ints from Cn and store those values in a vector. Repeat the previous but read strings this time. I think it is. I'm not going to do this. Okay. And other vector operations. In addition to pushback, vector provides only a few other operations, most of which are similar to corresponding operations on strings. Maybe I'll just quickly write it out. It's easy. What exercise is 3.3.2? Exercise 3.3.2. This is 3.14. And be 3.14 CPP. And cd vector. Okay, so I'll go int I equals 0. Then we'll go while cni, and I'll create a vector of type int, name it ivec. It is 0 in size. We'll go ivec dot push back I, and print for int I and I back, say for int C and I back, and go C out C. No. Okay, so I'll go with G++. So 1, 2, 3, 4, 5, 6, 9. 1, 2, 3, 4, 5, 6, 9. Great. And then I want to do the same thing. It must be 5, right? Yep. So let's copy this. We add in the string. We add in the string. S. S. This will be char C spec. And this spec dot pushback S, and oh, sorry. Repeat the read strings this time. I'll go string C. Then what else? Okay. So I guess that's about time, and